Idea of sampling distributions of the mean. We had this original population of 50 movies, the top 50 grossing movies of all time, and the population looks something like this, with a population mean, mu, of $383.1 million. Now, if we are interested in conducting inference, that means we're going to take a sample from this population and use that sample to make predictions about the population at large. But we had this idea that if I take a sample, maybe here's my random sample of 2, you would take a different 2 movies, we're going to get different means. So we explored what those look like. Here are sample means for samples of size 2. So everybody gets different samples of size 2, finds their X bar, their sample mean for their sample of 2, and this is what we get. Here were the means for 10 and for 20. And we made some observations. We're going to formalize those in this theorem. Probably one of the most important theorems in statistics, our central limit theorem. And this tells us what the sampling distribution of the X bars looks like. So it basically reviews what we had on the previous page. We notice the center of the distribution, the mean of the sample means, or X bars, is just the population mean. The spread changes depending on my sample size, and specifically the spread of a statistic is called the standard error, and you might denote what statistic you're talking about with a subscript. And that standard error for means is the original standard deviation over square root of n. So as n, our sample size increases, the variability from sample to sample will decrease. And then the last thing is our shape. If it starts off normal, then the sampling distribution is normal, regardless of our sample size. If it's not normal, then the sampling distribution will gradually become normal the larger our sample size. And for large n, kind of a typical guideline is if we have at least 30, then it's probably going to be normally distributed. The means will be. However, this really depends on the distribution of the original population, but 30 is a good guideline to be able to apply these results. If we wanted to sum this up in one quick statement, then we would say it this way. If we have a decent enough sample size, i.e. at least 30, then all the different X bars, I take a sample, you take a sample, we get a different X bar, they're going to be normally distributed, regardless of what the original population looked like, centered at mu, the population mean, with this variability, sigma over square root of n. So let's think about what some implications for this might be. So here, continuing with our box office example, and it says, would it be unusual to take a sample of 2 movies and get an average earnings of $425 million? Well, that depends on what the average earnings of samples of size 2 look like. So if we go up to our sampling distributions here, here's our samples of size 2. 425 is somewhere around here. So we'll notice, yeah, that's quite common. It's kind of right in the middle of all the values that we're finding. So we might make a comment like something like this. According to the sampling distribution, and that was on page 56 for reference, values of $425 million are not rare at all. They're kind of very common and almost centrally located in that distribution. What about if we had a sample of 200 movies? Would earnings of $425 million be likely? So checking it out, here's our samples of 20. Notice the spread is decreasing, so the chance of getting a sample that had 425 for the mean is far less likely in this case, in this distribution. So we might make that similar observation. according to the sampling distribution. And you'll notice I always abbreviate distribution here. Hopefully you've picked up on that. But according to the sampling distribution on the same page for n equals 20, values of 425 million are in fact rare in this case because the variability when we're looking at larger samples has decreased significantly. So it's very important to know what the distribution looks like for different samples of a certain size. So let's write that down formally. What is the sampling distribution for the mean? So here's our key phrase here. It's asking, what is the sampling distribution for the mean? So I'm going to write down x bar because there's my sample means, and we're saying what the different sample means look like. So these different x bars look like, and we have the central limit theorem above. It tells us they're eventually going to be normal if we have a decent sample size. So here, n is over 30, so we're okay. And the x bars are going to be centered at the population mean, which was at $383.1 million. And then the variability here is going to be the original standard deviation, which was our 141.8 million, divided by the square root of our sample size. Remember, that's our standard error. So this is a complete answer, what we're looking for here. Sampling distribution of the mean, you need to give all of this information. The statistic you're talking about, and then the shape, center, spread. And as a reminder, I'm referencing this central limit theorem results that we've been exploring here. Sample mean has this shape, center, and spread. Now, if you would like, you might consider working out the standard error off to the side to have handy for later. So this last term here is our standard error for the mean. If you work that out on a calculator, you're going to get 23.9686. So that describes the size or amount of variability of the sample means from one different sample to the next. Okay, again, highlighted answer is what we're looking for. Sample means have this shape, center, spread. Now let's check out part D. What is the probability of random sample of 35? So now I'm thinking, hold the phone. I know what random samples of 35 look like. This tells me what they look like. They're normally distributed. I know how to find probabilities for a normal distribution. We're gold. We know how to do this. All right, so let's write the question here. The probability, and we're talking about the average earnings of 35, so I'm going to use x bar now instead of plain old x. I'm not talking about one movie, I'm talking about 35, so I need the average of 35. And specifically between 380 and 385 million. Okay, now this is familiar territory. All we need to do is convert to our standard unitless case, and then we're good to use normal CDF. So observation minus the mean. Remember, my variable now is the sample mean. So my sample means look like this. So the mean of that distribution is 383.1 million. Now this is the only part that changes. The standard deviation or standard error or spread is this second term, this 23.9686 term. And instead of x bar for the mean, I'm going to switch this to z because now I'm calculating z-scores. I'm switching to that common unitless scale. Same thing, I have two z-scores, so I need to convert both of them, two observations. So I need to convert both of them to z-scores. And show that calculation, that conversion. And notice I'm not using the original 141 for the standard deviation. I'm using the standard error or standard deviation that describes 35 movies, not individual movies. And That's going to give you a lower z-score of negative 0.1293 and a larger z-score of 0.0793. Remember, when we know the z-scores and we're looking for a probability, that's normal, CDF. And we're going to plug in our lower and our upper. And if you want to pause and take out your calculator to double check, you should be getting a value 0.0830. All right, let's do another example here of how this might apply. So this next example tells us, according to AAA, that motorists aged 16 and older have on average drive almost 30 miles a day, and which is over 10,000 a year, and the distribution of distances is unknown. I could not find the standard deviation for that study, so let's assume it's 10 miles per day. So we've got X, how much we drive each day, has some unknown distribution with mean 29.2 miles per day, standard deviation 10 miles per day. So this first question says, find the probability a randomly selected driver, I want to highlight or emphasize that, one driver, travels less than 25 miles per day. So in my probability notation, I'm going to use just plain old X, not X bar, because I'm talking about one driver. So X less than 25. And if you're not thinking too carefully, you might just carry on with the way we've been doing things. Convert that to Z is less than observation minus the mean over our standard deviation, or the probability that Z is less than negative 0.42. Again, I know Z, I'm looking for a probability, so we'll go with normal CDF. And less than, that means our lower is going to be negative infinity up to negative 0.42. And we're going to get a value of 0.3372. All right, so we did all this work, but I hate to tell you it's incorrect. Don't erase it. It would be correct, but we're missing one teeny, very important piece of information. Right, that very important information is this question mark. What is the shape of this distribution? I'm only allowed to go through this process we just did if the random variable is bell curved, if it's normal. So I'll make that comment here. We actually cannot answer this question because we do not know if the distribution is normal. Okay, if we did know that piece of information, if we knew it was normal, then we could go through this process and be perfectly fine. However, watch out for that. We need to know if the distribution is normal. So part B, suppose instead of looking at a randomly selected driver, we're interested in a sample of 40 drivers. And we're interested in the sampling distribution of the mean for 40 drivers. So there's our key phrase again, sampling distribution of the mean is saying, hey, tell me what the sample means look like. So X bar, say what statistic you're about to describe. So the sample means look like, and 40 is well over our guideline of 30. So I can say the central limit theorem kicks in, and the shape is normal. Even though I didn't know the shape or the distribution for individual observations, the central limit theorem guarantees that by samples of 40, it's going to be normally distributed. And they're going to be centered at the population mean, 29.2. the variability from sample to sample is going to be 10 over square root of 40. So that's a perfectly fine answer here for the sampling distribution of the mean, describing what those look like. Now let's go ahead and work this standard error out just to have handy for the next part. So 10 over the square root of 40 is going to give you 1.5811. And then checking out this last part here, we're still asking about less than 25 miles per day. That was the same as Part A. Part A asked about less than 25 miles a day. But the difference between the two, Part A was 1 driver, Part C is a random sample of 40 drivers. That's the difference between those two questions. So individual drivers, we didn't know what the shape of the distribution looked like, so we were unable to answer that question. Part C, we know that averages start looking normally distributed, so now we can answer this question. And in fact, right here, we just described what averages from samples of size 40 look like. So let's work this out. Probability x bar is less than 25. So notice the difference in notation. Here x, because I'm talking about an individual driver being less than 25. Here it's x bar because I'm talking about the average of 40 being less than 25. So let's carry on. Let's convert that to our z-score. In my mind, I know I'm allowed to do this because I said x bars are normal, so I can use z-scores. And I've got my observation of 25 minus the mean of 29.2 over my standard error, standard deviation, or spread. Make sure you're using the one associated with averages of 40. Not the one associated with individual observations. So this should be 1.5811. Or in other words, the probability that z is less than negative 2.6564, or normal CDF. Again, this is less than, so our lower is negative infinity up to negative 2.6564. And if you work that out, you're going to get 0.0039.